All right, everyone. We're here finally at a long-awaited tool, one of the most powerful tools that you're going to be using in this introductory circuits analysis lecture series and class in college. It's nodal analysis. It is personally my favorite way of solving circuits. There may be case scenarios where it's not the most effective way, but it's definitely one of the most intuitive. So these next few videos are going to be a lot of practice-based videos. We're going to just go drill through problems, work through examples, and yeah, that's how it's going to be, much less so a lot of the mechanical workings and a lot of the mistakes that I've made during class and a lot of my friends have made during class, just so that we can make everything super clear. So first, I want to show you the algorithm of nodal analysis. There's 3 steps. The first one is to identify ground and the nodes. So if you are given, for example, a circuit that looks like this, and you have resistors and resistors and resistors, and you want to find, you're going to want to find the voltages, and there's a voltage right here, the voltages at this point right here, this point right here, and this point right here. So normally it would be given to you which nodes you're going to want to find, but obviously in the real world you're going to be wanting to find some nodes that you want to analyze, etc. Maybe this node is not that important, but for context of this class or this video lecture series, we're going to probably be solving for every single one of these nodes. And then you want to identify a ground. So a good ground would probably be where it would be easiest to assign a 0 voltage, and you're going to see why that's important soon. So that's step 1. The next thing is to write KCL equations. Now, what do I mean by that? If you have 3 variables, like take this in consideration, this example right here, then you're going to need 3 equations, right? And so a KCL equation basically is based off of KCL, Kirchhoff's current law, which is the sum of the currents is equal to 0. Now, the interesting thing here is we're going to get I1 plus I2 plus I3 equals 0, or something like that. Now, the interesting thing that I was about to say is that we have these currents coming out of each node, right? And we have to treat each node as its own individual, right? So we're gonna have 3 of these guys. So I would call it node 1, node 2, and node 3. And at all times, I would make the default as going outwards, okay, unless explicitly told otherwise. And we're going to go through examples like that. And we need to write these currents in terms of voltages, because that's what we want, right? We want voltages, not currents, okay? So we know we're going to also employ, so I guess I say write KCL equations, but in reality, we're also using Ohm's law. So we're going to employ Ohm's law in the idea that we want to find this current in terms of voltage. That's why nodal analysis is so powerful, and its counterpart, loop analysis, is so powerful, because you get to find each variable in terms of the other. So in this case, we're going to get I is equal to V over R. So each one of these guys is going to have like this, okay, where R is some arbitrary number, and then we get it to 0. And then from there, we're just going to simplify and solve. Plug it into your calculator. Please use your calculator for this. Because this is a system of linear equations, we are going to be using coefficients, I mean, not coefficients, matrices, what the heck. So we'd have A, B, C, D, E, F, G, H, I, and we'd have some arbitrary constants, y1, y2, y3, and v1, v2, and v3, right? And I would highly encourage you to use a TI Inspires or TI-84, something that can do a linear solve, system of linear equations solve, so that you can find these guys right here, okay? Because if you're going to be doing these by hand, that is a waste of your time, and it doesn't truly make you understand circuits. It just makes you understand how to do matrix vector multiplication and solving ax equals b, which is a linear algebra topic. So yeah, and it's also nice to just write it in this form, so that your professor can see, hey, I have the coefficients and stuff like that, and then I'm going to solve it using the calculator. And yeah, and then a little step, I guess a step 4 would be to replug. So what do I mean by replug? Once you find all of these voltages, then that means once you plug the voltages in here, you should get 0. If you do not get 0, then you must recalculate. There is something wrong. So that's the good thing about nodal analysis, is it can provide a check system. So we're going to do the most simple circuit that you can't use, classical methods like what we were talking about, resistive circuits and etc. We can't do that because we have 2 batteries. And yeah, so let's go ahead and do this example. So step 1, we're going to identify nodes and ground. Okay, it seems to be that this is a nice ground because we obviously cannot ground V1. If we grounded V1, then we would just call V1 0 and we'd be finding this, but the problem is specifically wants us to solve for V1. So we're going to call this guy right here 0 volts. So now we're going to start writing our KCL equations. Now notice we only have one unknown, so we're going to only need one equation. So I'm going to call this guy node 1. Have node 1 right here. Now let's start summing up the currents. So we have one current going out this way, right? And one current going out this way. So we'll call this one I1, we'll call this one I2, and then I3. Okay? So we want I1 plus I2 plus I3. But we know that's not useful, right? Because we don't know those currents. So let's turn it in terms of these voltages. Now, this is very, very, very important. When not given a specific direction, you are going to do it outwards of the node, okay? You can do it inwards if you want to, but you just need to remember, if this is more intuitive to you, then by all means do it. But I am always going, as I said in previous videos, I am always going to be doing it current going outwards. So we're going to go ahead and do that. Now remember, Ohm's law is V over R. So that means, but this V is a voltage difference, okay? So a voltage difference from point A, which is our node of interest, to point B, which is whatever the ending power source thing is. Or this could be nothing. It could just be 0, as we'll see in one of these currents. So let's say I1 is going to be V1 minus, and it's minus because we're dropping in voltage right here, right? Because when we go from this point right here to this point right here, we get plus 3 volts. We have plus 3 volts here, and then we have, I'm sorry, not plus 3 volts. We get the difference between whatever V1 is minus 3, right? Because this is going to show the difference between here. I think that makes sense. I hope that makes sense. And then, so we're going to do V1 minus 3 over, and then over a resistance, over the resistance of this path right here. And so the resistance in this case is 3. Now let's do I2, same thing. We're going to go from V1 to 5, find the voltage difference between these guys right here, and then divide that by the resistance. Now here we're going to do the exact same thing. We've got I3, V1 minus 0 this time because we're directly connected to ground. Okay, I'm going to divide that by 2. Now let's assemble our equation. We get N1 is equal to V1, sorry, not N1 is equal to, but the KCL equation at this point is equal to V1 minus 3 over 3 plus V1 minus 5 over 4 plus V1 over 2 equals 0. And simplifying this down, oh, by the way, I will in the future not be writing these down. I'm just going to simply be looking at this picture and saying, oh, we have V1 here. We have a source right here. I'm going to find this current in terms of that voltage immediately. And then right here, we're going to have to find a common factor. We can just multiply everything by 12. So we're going to get 4 times V1 minus 3 plus 3 times V1 minus 5 plus 6V1 equals 0. Now please be careful. I make so many mistakes doing this as well, and it really does suck, you know. In fact, let's just make sure that everything is correct. So we got 12 over 3, yes. Okay, yeah, everything looks good right now. So we're going to do 4V1 minus 12 plus 3V1 plus minus 15 plus 6V1 equals 0. And we're going to get 13V1, 13V1 equals 27. So V1 is equal to 27 over 13. Or, using the calculator, we're going to get about 2.0769 volts. Okay? And doing step 4, which is the check, we're simply just going to plug in this number into this equation that we had made right here. So, and plugging this into the calculator, we get approximately 0, which is what we want. So the answer is 2.0769 volts, and we are going to do more problems like this in the future, a little more complicated, because there's a lot of different types of these kinds of nodal analysis problems that you will be seeing. Okay.